in Edinburgh now. That are soft matter. Polymers, micelles, suspensions, emulsions, foams, liquid crystals, and this may or may not mean much to you, but in fact, these are things that we encounter daily. So an example of a polymer solution is an engine oil, so that consists of long polymer chains in a short molecular solvent. Micellar systems, which are also polymer-like structures made out of soap molecules, are in nearly all brands of shampoo. And suspensions, or toothpaste suspension, etc. I can go on down this list. So you can see why these are called soft matter. They're mostly pretty soft. But there's also a whole branch of physics connected with the kind of high-tech end of soft matter. So all polymers, all plastics rather, in processing are go through a molten stage or a semi-solid stage. Additives very similar to what you have in shampoo are used in things like this oil pipeline down here. Pharmaceuticals, drug delivery, etc. Foams, foams get used in cleaning up after fires and things like that. And liquid crystals are in every single one of your laptops and mobile phones. So, the picture as physicists we can have of these systems is to back off from the molecular detail of exactly what's in there and try to classify them into broad categories. And then within each category we're hoping to find universal types of behavior, which does include the phenomena I'll show you later in this jar here. So polymers we think of as molecular spaghetti. Suspensions of colloidal suspensions, or these kind of dense suspensions here, are basically molecular ping-pong balls or microscopic ping-pong balls, small hard particles suspended in a solvent such as water. Liquid crystals are also like that, but then you have to think of them as needle-shaped structures here. So today I'll focus on the middle one, suspensions, the baseline model, molecular ping-pong balls, and how does the presence of this structure, the fact that I have some kind of organization of these solid particles inside my suspension, how does that control its macroscopic behavior, and in particular, how does it control the flow behavior, which, as we should see, can at times be spectacular. So one of the main intriguing features of the flow behavior that we'll see is the presence of an effect like a traffic jam. It's a jamming phenomenon. And so what I want to do next is show you some other natural phenomena involving jamming and unjamming. So the top right is fairly familiar. Bottom left is actually a log jam, literally. You're in Canada, so you should know all about that, but most Europeans have never seen or heard of a real log jam. This is a landslide, and as you can see, this is something which was solid but is now turned into a fluid, and obviously if that happens near you, you need to get out of the way. This is only an animation, because this kind of thing, when it happens, you're rarely waiting for it with a camera crew. This is a grain silo, and this is something you really don't want to happen in your grain silo. It's to do with the build-up of stresses in the granular packing, quite similar, in fact, to the kind of thing I'll be talking about later on, and then a catastrophic unjamming in that final frame, as you saw. So, on to the main deal, dense suspensions under flow. So, let me show you a couple of movies. Get them both running once. Okay, so on the left here, this looks like a computer simulation, but it's actually an experiment. So what's done here is you have these microscopic colloidal ping-pong balls, roughly 1 micron particles, in a solvent, and you're shearing them. So you have a moving plate across the top here, which is moving to the right, and a stationary plate at the bottom. You saw here a similar movie, this time computer simulation in 2 dimensions. I'll show that one again. So you can see here, this also, so the blue arrows here are showing you the average velocity. So you have this shear effect. but you can see this has a kind of stop-start motion to it. So the fact that this is an unsteady flow is all part of this jamming phenomenon that you get in dense suspensions. So the presence of this kind of behavior is actually quite mysterious, at least in terms of the standard way of thinking about these systems, and that the fact that it's the models we had until recently anyway were quite constrained as to what they could predict, and they could not predict some of the phenomena that I shall be showing you. So let's go to the baseline model of fluid flow, which is Newton's law of viscosity. So you can read about this in Latin, should be. So we have a stress. So if I have a moving plate and a stationary plate, I have a stress force per unit area horizontally on the top plate here. The displacement is r dt. So r is the strain rate, so that's the speed of this plate divided by the depth of the sample, and the area of the top plate is a. So Newton said, okay, the force is proportional to the rate of strain, in other words, proportional to the amount of shearing you're putting in. So S equals nu times r, nu, Greek letter nu. If you want to read that as V for viscosity, that's fine too. In the field, stress is usually called sigma, strain rate is usually called gamma dot. I'm trying to be a bit more sensible than that. So stress as a function of rate, strain rate, r. Newton's law says that stress is proportional to strain rate. So the viscosity is the slope of these lines here, and it varies from fluid to fluid, but in each case you have a straight line. So that is a class of behavior which is widely seen and is called Newtonian flow behavior. However, other things are also seen. So non-Newtonian fluids have a stress as a function of rate which is not a straight line and can have all kinds of curvature and variation, various names, shear thinning, shear thickening. As you can imagine, those describe the case where the stress is curving downwards or curving upwards. And the case I'll be talking about is extreme or discontinuous shear thickening. So there are many examples of these. The ones on the left, water, olive oil, honey, molten glass. These are Newtonian. You might not think that about melted glass, but it is. It's extremely viscous, but Newtonian. Honey there, I mean the kind of runny kind of maple syrup, better example. These ones on the right, including saliva, these are non-Newtonian. These will have non-linearity in those curves. And the mystery is why the molecular ping-pong balls, the dense suspension, why is it ever non-Newtonian? Because the first pass theory seems to constrain it in such a way that it must be. So that's part of the story. I should try to tell you. So, it looks like I'm getting through this talk very quickly. Unfortunately, I'm going to focus on how we explain it. So, shear thickening suspensions. Okay, so first though, I want to gather the phenomenon. I want to tell you what it is that a theory should try to explain. Shear thickening suspensions are liquids that solidify at large stresses, hence the title. Goobleck, if you go to popular science web pages and many science fairs and all kinds of events and school lecture talks, which I give myself, Goobleck has become the word for this material. This is cornstarch in water here. I'm just about to show you what it does. And based apparently on this remarkable book by Dr. Seuss. So, in which the world is apparently invaded by non-Newtonian fluid. I've not read this book, I'm afraid. I'm sure many of you have, but it's sort of sounds a rather surreal night. Anyway, let me show you some. So, what we have here is cornstarch suspension. So you go and buy cornstarch, and custard powder is the same as cornstarch, it just has yellow dye in it. Some sugar, hence bulletproof custard. I could have said bulletproof cornstarch, but that would be an even weirder colour title. So I'm going to drop this stick in here. So the idea is that this is a fluid if I'm very gentle. So I'm barely touching it. I can move the stick around. You can see I can wobble it. And it looks pretty runny, maybe a bit sticky. But then it's difficult getting the stick out. Try this. Okay, so this is an unusual fluid. I've actually smashed the beaker here, and it's not leaking out. But this is this. Now you can also see this is that's gone in. Okay, so it's doing what I said in the title. If you're gentle with this, it's quite runny. If you're violent with it, it just resists. So as somebody who recently, for the first time, became the owner of a dog owners will know what it's like to have a dog that has a different view of where you're going on your walk from you. It doesn't matter. The harder you put it, the slower it goes. So this is really the same. So let's be gentle. I'll try to be gentle with this first. But even now, you see. Good. Let's leave that. Let's see what happens. So this may fall off at some point. Having already broken the beaker, I shouldn't play too much. So you see there's lots of very interesting flow instabilities here. So what's happening then is that the fact that this is harder to flow when you push it hard has a bunch of phenomena associated with it. One is that the transition from being easy to flow to being hard to flow can be very sudden. And the other is that the resulting flow can be very unstable. And if you see how wobbly the front of this kind of sheet of cornstarch is here, this is not like the flow of any Newtonian fluid. Even if I slow down the movie, you just don't get this kind of instability. So see if this will stay without. Try and do that a little bit longer. It's going to fall off. Right. Now we do. What's that? Oh, I see. Yeah, well, I want to go back to my slides. Oh, thank you. Yeah, so you can place your bets as to when that's going to fall off during my talk and scatter bits of wet. Okay, so this is the Daily Mail, one of the UK's most reputable newspapers. Talking a few years back about bulletproof custom. So how it works, you can read how it works. The traditional bulletproof vest is made of laminated Kevlar, and Norman Wagner in the University of Delaware has got patents, and the US Army is developing bulletproof clothing, which has much less Kevlar, and between each layer of Kevlar and the next is a layer of stuff very like this. So the idea then is that the bullet is like the hammer, it hits it and it solidifies, and that spreads the load out a much wider area, so you can get away with much less Kevlar and much less damage when you're shot. So bulletproof custard is their phrase, but I was very happy to borrow it. And of course this isn't custard, but it is exactly what you get with custard powder if you put too much powder into the water. You'll also see things like this online, which is the same. This you need a lot of cornstarch, but it's quite fun if you can get it.